The last slide was talking about analyzing data. We're talking about the scientific method. Two purposes. One is descriptive data, to sort of explain, let me rephrase that, to describe what is going on, right? A description. That's what we're going to start with. And then we're going to move to inferential statistics, where we actually test hypotheses. And now I remember talking about this. Last two steps. Once you, hopefully doing inferential statistics, reach a conclusion about a research question or a hypothesis, the last step is to draw a conclusion. So what does this mean? You've collected all of this data, you have the numbers, you've followed the steps in the process, but what does it actually mean? What is the outcome? Then how does it relate to your broader question? So we're asking ourselves whether or not the results that we observe support the research hypothesis. Now I have to sort of have a digression here, because social science is not a hard science. We are not creating laws of physics here. We still talk about things in terms of theories and whether or not data supports a theory. We have to be very careful about using language that says we have proven a research hypothesis. Because if you prove something, it has to happen every single time. It has to be causal. There has to be a cause and effect that is, you can explain exactly why it happens and how it happens. And trust me when I say this, we don't prove a lot in the scientific method. We really do not. And even when we do think we've proven something, we find out that sometimes that proof is condition specific and it's different in different places. So let's think about physics for a second. In physics, the things that we learn are typically about motion. Objects in motion tend to stay in motion unless you interacted with a counteracting force. Okay. How do we know these things? Through crash test dummy videos, right? Or think back to the idea of gravity. How do we know that gravity exists? Well, probably some scientist had a cat, and that cat just kept knocking shit off the table all the time. And they're like, oh, look, it falls, gravity. Well, gravity exists under certain conditions. Conditions that we only know about where? On Earth. How many other places have we been? Now you're thinking, you're like, well, there's the Earth. Where else have we been? Like, let's go with humans first. Where? The moon. Right? So our observations about the effects of gravity have taken place 2 places. 3 if we want to count space as a place. Right? Or in a thing in space. Okay? So let's not say we know things, right? Science is useful because we want to understand how phenomenon happen, but even then we're not really sure we can prove anything. Can we even comprehend what's going on out there in space? Okay. So we have to remember that there's this important distinction between what we're doing and what we know. Like this idea of like a universal truth that's out there. We want to arrive there, but we can't really ever know. And that was to go back to that idea of epistemology, right? All right, last thing. In the scientific method, you've done all this work, and then you have to write it up. You have to communicate your findings. You have to explain what it is you did, your process, your conclusion, and then you have to share it with the world. And it's important to share it with the world. Why? That was an actual question, sorry. I know I do these things sometimes. Why do we need to share our results with the world? So why? So others know about it? And what are they going to do now that they know about it? Maybe we're trying to change opinion. Maybe it'll help their own research. Maybe they'll redo what we did and confirm whether or not we were correct or not. Right? This is all part of a conversation. And this is what you're going to do. This is what you consume in your classes. You consume these communications about the scientific method. People do a study, they write up the results, they try to publish it in a journal. The function of the professor is to curate. We curate all of the books and articles and things that are out there in the world. We curate it down and we say, read this. This will help. This will help you to understand your topic or your question. So the goal of this class, at the end of it, and why you have to write a research paper, is because I'm teaching you how to test a hypothesis, and the last thing you have to do is you have to share your findings with the world, or me. Okay. So that was finishing up last week's class about why we do statistics and why you're going to take this class. What I'm going to do today is I want to actually start talking about data, about numbers, about the stuff you're going to use this math that you're going to learn on. And as we said in the previous slides, there's sort of two types of analysis. One is descriptive and one is inferential. Well, in order to do the inferential part, where we actually test the hypothesis, I have to teach you the descriptive stuff first. So back to this idea of a variable. Remember, a variable has to vary. It has to be able to take on different values. Last class we talked about something about that's common to all of us that doesn't vary, that we all live on Earth, that we're all human beings, I think. However, there are things out there that are used in math but aren't actually variables, that are constants. Anybody think of a constant? It's when you've learned. I'm not asking you to know anything you shouldn't already know. A constant is a number that does not change. You're going to feel really dumb when I say it out loud. I even referenced it last class. Pi. Pi is a constant that does not change. It is 3.14159 on forever, right? Anybody know what E equals MC squared is? No? Anybody want to associate E equals MC squared with a person? If you don't know who it is. Can we just talk about who came up with it? Einstein came up with it. Okay. So it's something about physics, right? Einstein's theory of relativity. Energy, E equals mass, so how much something weighs, times C squared. Anybody know what C is? It's another constant. C is the speed of light. And this is why we can never really test Einstein's theory of relativity, because we can never make anything go the speed of light. It would take all of the energy on Earth ever consumed in its billions and billions of years to get an object up to the speed of light. Not possible. Stupid Star Trek has ruined your conceptions of possibilities of physics. Okay? But the C is not a constant. The M, which is mass, is what? A variable. Because we all have different masses. This is exactly the reason why we wear seat belts. Force equals mass times acceleration. Where does the acceleration come from in a car? How fast you're going, the speed of the car. And why do we wear seat belts? So we don't what? So we don't fly out of the car, right? Because if your mass is not tied to the car's mass, when you stop suddenly at 50 miles per hour, the car stops, but you keep going. So the purpose of a seatbelt is to keep you attached to the mass of the car, so that when you hit an object, A, you don't get expelled from the car, but B, you have a better chance against that object when you weigh 5,000 pounds than little old 200-pound you, right? Okay. If we're going to have variables, we have to recognize that variables can come in all sorts of shapes and sizes. The best type of variable is known as a continuous variable. A continuous variable, in theory, has an infinite range of numbers. And infinite can go one of two ways. This is a number line. And how would I represent infinity on a number line? Anybody remember what infinity looks like? It's a sideways 8. Or it's a little fish. And we can go to positive infinity. And we can also go to negative infinity. So that's one way numbers are infinite. They can be infinitely large or infinitely negative, but still really large. Anybody know what the second type of infinity is in a number? What do you think? Yeah. So between 0 and 1, how many numbers are there? Because don't decimal points go out to infinity? You guys know this because anytime you go to a professor and you're trying to round, you're like, well, if you look at this number with 10 decimal points, you're like, and if you round this number up, and you're like, wow, you got to round the 10th digit up to get the 9th digit up to get the 8th digit. Like, whew, that's a lot of work, right? Because you can find out, you know, to the 9, and then you're like, what if I round that one up after it? The 9 becomes a 1, and then you're just carrying the 1 up through, and then you get your A. So there's infinite space in between numbers as well. Which means when you measure something, you have to make some choices, right? You have to make a question about how you're measuring it, how precise you're going to be. The temperature in this room right now is 72.3 degrees. Why do I need the 0.3? Do I need the 0.3? Why is there a 0.3? Like, oh no, it's a little too warm in here. I got to get it down to 72.1. So when you're talking about continuous variables, precision is a question. How precise do we need to be when we're measuring something? Think of money. The next time you're at the gas station, look at the price of the gallon of gas on the gas pump. What's weird about that? So when we use money, how many decimal points do we typically use? 2. They're called cents, right? Out of 100. A centimeter, right? So cents. When you go to the gas station, what is the gas price? Right. They always add that extra 9 at the end of it. Why? To make it look like it's 1 cent cheaper. That's an artificial form of precision. It's just trying to mess with you. It's just trying to convince you that gas is a penny cheaper than it actually is. It's the same thing as why things are at 99s. So if you watch people, this always comes up every few years, we should get rid of the penny. And you know why we should get rid of the penny? It costs more than a penny to make a penny. It costs us 1.2 or 3 cents to make a penny. So there is depreciation in a penny the second it is made. It's kind of like buying a new car. The second you buy a car and drive it off the lot, you've lost $10,000. So make sure you wreck that new car nice and good, okay? All right. But when you mint a penny, your penny, which is at face value is worth 1 cent, costs you 1.2 cents to make. And so people will constantly saying we need to get rid of the penny. But what's the side effect of getting rid of the penny? What happens to our precision in our money? To what? What's the next precise instrument we have with money? Everything will have to be rounded up to a nickel. Right? Okay. So precision in how we measure affects the variables in the data that we create. Right? The fact that we have a thermometer that goes to the 10th degree Fahrenheit, the fact that in our money we have coinage, we have fiat, actual physical coinage, down to the hundredth with a cent. Okay. These are decisions that get made in society. You as a researcher, when you're measuring something, also have to make these decisions. Whenever I travel outside of the United States, I don't understand the concept of Celsius. Like, what's the difference in Europe between 7 and 8? Because we're raised with greater precision here in the United States on the Fahrenheit scale. Right? Like, I know the difference between 80 and 75. I don't understand the difference between 10 and 11. Apparently there's a difference because the people in Europe are perfectly fine with this idea of, oh, it's going to be 10 today. Wow, I really hope it doesn't get to 11. Whew. So a continuous variable is one in which we can have greater precision. It gets a little messy because of, the concepts of dual infinity, infinity out, and also infinity within. Another type of variable is known as a discrete variable. And a discrete variable takes away that concept of infinity within. There is nothing between two values of a discrete variable. I have 2 children. If my wife was pregnant, I wouldn't have 2.5. And I'm sorry, dog and cat people, but they're not kids. Your dog is not half of a person. Right? I have 2 children. And the only way that number can change would be to add more whole children or to delete a couple of the children. Right now, Abby's going to get the boot. She's 9, and I don't think there's any change in Abby. John's only 5. I got some space and time with John. I can fix John. Abby's a goner. Can't happen. Abby goes first. All right? Whole children. Right? So you can't have halves of objects. If we're counting objects, you can't have half a car. Well, actually, you can. I've seen that happen before. Just cut the car in half. You got half a car. And they still drive. Front-wheel drive cars will drive if you have half a car. But is it half a car, or is it just like a subcompact? And is it still a car if it only has two wheels? These are measurement questions. Okay. So it's an exact measurement, although there are a few different ways in which you can have discrete variables: nominal, ordinal, or dichotomous variables. So I'm going to talk about the differences between those. A nominal variable is a name. Now, we still assign a number value to the name, but there's no relationship between the number that is assigned and the name of that number. Right? So let's say I want to measure everybody's religious preference. And I ask you, all right, look at the list. Which one of these are you? Pick one. He's a Muslim. Okay? So in my data set, I have to put Muslim for him. Now, I could write the word Muslim. I could do that. But when you're doing statistical computing, it doesn't like words. It really doesn't like words because it's looking for numbers. So you are the first one. You get to pick your number for Muslim. Pick a number. 10. Anybody here want to be Jewish today? The holidays are coming up. All right, Marina, you're Jewish. What number? 4. Anybody in here Catholic? Pick a good Catholic number. That's a bad Catholic number. What's the good Catholic number? The good Catholic number is? Why? The Holy Trinity. Good Catholic. All right? You just assign a number. Why? Because the computer wants a number. 0, 1, 2. Now, does the number represent a value? Is Muslim 10 times a Shinto? Does it take 10 Shintos to make a Muslim? Right? I guess you got to get them all together and be like, all right, 10 of these for one of you. It doesn't work that way. The number is just, again, think of it as code. Right? It's just telling the computer what to associate the name to the number. All of these are names. Okay, so you have to sort of have identifiable, clear categories. What makes a person Jewish? She said she's Jewish. Is she Jewish? Are you Jewish? No, I didn't think so. All right? There are actual rules to this. Right? What's the easiest way to become Jewish? You had to be born into it. If you want to be Jewish, you guys got to go out and get a Jewish mom. Because that's the way you're automatically Jewish. You have a Jewish mom, you're born, you're Jewish. Not enough to have a Jewish dad, Jewish mom. Okay? Or you can convert. Okay. There are categories here that are defined, right? Catholics, they have a process, right? Yeah. You don't just get to be like, hey, everybody, I'm Catholic today. Right? In order to be a recognized Catholic, what do you have to do? You have to be baptized and then eventually go through what? Communion, confirmation, right? You get your Catholic name, pick a name of a saint. Okay? There are requirements to being a Catholic. I don't know enough about being a Scientologist, so I guess you just have to like pay some money for some classes and you're a Scientologist. There you go. But because this is science, when we make these categories, we're going to have to defend how we classify things. Is there anything up there that's missing? There's a lot of them that are missing. Like the spaghetti monster people, the Pastafarians, that one's not up there. Jedi is not up there. Right? There's a lot that's not up there. There's also an assumption that everybody has a religion, or everybody only has one religion, right? Well, on Tuesdays I'm a Buddhist, but on the weekend I'm Jewish, because I like to start my weekend Friday at sundown. All right. Those are nominal variables. They're names. An ordinal variable, still names, still whole categories, but the categories themselves have an order or a sequence to them. The idea behind ranking, right? So the numbers, again, the actual numbers do not matter. But what matters is the sequence of the numbers. So I could assign 1 through 5 numbers. They have to be in order, and they have to match the order of the options, right? But I can change those numbers. I can change the centering of those numbers. I can make neutral be 0, and then a positive feeling be a positive number, and a negative feeling be a negative number. Do whatever I want with the numbers. The only rule is that the numbers have to be in a sequence. Okay. A few other things about these for ordinal variables. If you can, we like to have an odd number. It usually should be symmetrical. So if we fold it over on itself, it matches on either side. And we really like it that there is a I don't care category. All right. What are your feelings towards Pastafarians? Well, first of all, you don't know what a Pastafarian is. Second of all, you don't know if it's real or not, and I'm just messing with you. And so you might not want to be like, oh yeah, I love the Pastafarians. You have to have the option of going, I'm kind of neutral towards them. I don't know anything about them. I don't know if they're good or evil or if they eat babies or what they do. So I'm just going to sit this one out. The last type of discrete variable that we're going to come across has a few different names. A dichotomous variable. That sounds really painful. I had to go in and get my dichotomous variable excised. These are also known as binary, or my preferred term, dummy. A dichotomous variable, a binary variable, a dummy variable attempts to measure the presence of a trait. Now the example that I use is male. And somebody's going, that's not usually what we ask people, right? If I want to determine whether or not you're a male or not, what do I typically ask you? What's your gender, right? Isn't gender the polite term for whether or not you're a man? So why didn't I put gender up there? There could be a lot of genders. Well, what does it matter if you're male or you're not? Right. So tell me why, instead of putting gender up there as an example of a binary variable, I didn't put gender. Binary does mean two. Either you are or you aren't. But the measurement is of what? The presence of the characteristic. Okay? So gender is not a good dummy variable. Because whether or not you have a gender, kind of everybody's gender should equal 1. Everybody should have a gender, right? Although I know it gets messy. Okay? A good dummy variable is like a light switch, but not the light switches in these rooms, because these rooms have bad light switches. But a traditional, real, honest American light switch, right? It's got a lever sticking out, and you flick it up or down. So male is a good example of a dummy variable. Now, how are we going to say something is a male or not? Could we have different definitions of what makes somebody a male? Okay. Name one. Come on, say it. Genitalia. A penis makes a person a male. Right? Okay. There we go. There's one definition. What's another way that we can define somebody in terms of maleness? A beard. If you have a beard, you're a guy. How's that any different than having a penis? Right? It's a physical manifestation. Let's get even more simpler. How do we know whether or not we should expect them to grow a penis or a beard? No, trust me, I failed the name test quite a bit. You're all encoded, right? Your chromosomes, okay? In a pairing, females have XX, males have XY. We actually have less chromosomes than a woman. We lost the extra little leg. You could use that as an example, right? But no matter what you do, you have to have a definition. And this is where people are starting to argue about gender, right? Because the argument against using gender as a binary variable is what? Gender's not binary. That's the argument. And we ourselves had 3 different ways in which to measure gender. Right? One at the biological level, one with an appendage, and one with the ability to grow hair. Well, guess what, ladies? If I pump you all up with enough testosterone, you're growing some nice thick beards. And gentlemen, if I pump you with enough estrogen, I can make you grow some stuff too. Right? So, the argument against viewing gender as binary is that it can get complicated. What could we do with that? We could take something that originally we think is dummy and we could change it into nominal. Right? We could say, this male, not male thing's kind of hard because we have somebody that's biologically female that has a beard. And we could create different categories. Right? And we can do male and female, and we can do female to male, and we can do male to female, and then we could just do like XXY, because there are people out there who are born with both chromosomes, they're trisomal, and they have an extra Y in there, or an extra X. There's a runner from South Africa. She was born with a Y. Guess what the Y helps her with as a track athlete? She's pumped full of testosterone. And people are arguing, well, is she a woman or is she a man? Genetically, she's this thing, XXY, whatever the scientific term for it is. Outward appearance, she's female. Absence of a penis. But chemically, when you run her blood, she comes back as a guy because of her levels of testosterone. And her testosterone is too high for what they would expect out of a person who is a woman. So they think she's doping, but she's not. She has a genetic condition. So measurement can get really complicated. Like, you all are like, hey, this is just easy. You're either a man or you're not. But it depends on your level of precision. How precise are you trying to be? Okay. So nominal, ordinal, interval. Whenever I include a slide that has your book cover in it, it's because I ripped it off from the book. And I want to include this last one that they talk about in the book. Howard talks about a ratio level. A ratio level is an interval variable with a true 0 point. Don't really use these a lot, like, because I like the idea of a continuous variable. Continuous variable has a 0 point. If we think of money as a continuous variable, are there days in which you have no money? You better be poor college students. Okay. So ratio level is kind of the same, but whatever. I have to acknowledge that the book uses something different. Interval variables with a true 0 point. So you can think about these in terms of starting at 0 and going up. There's a variable type that I love. It's called a feeling thermometer, and it asks somebody to give a score between 0 and 100. That's an interval level variable. Right? You have 101 options between 0 and 100. All right? So from 0 to 100, how much do you like President Trump, Hillary Clinton, Mike Trout, Denzel Washington? You know, do some example. And then you give them a number. And it really allows for a level of precision, 101 different outcomes. But it turns out people actually just pick something rounded off to 5, and they like to do 0 and 100 a lot. Actually, they're more likely to give 100 if they like somebody, and they're less likely to give a true 0. So they're kind of nice, and they're like 6. It's like, dude, just say 0. We know you don't like Hillary Clinton. Give her a 0. 6, 4. All right. One more thing about how we measure. We get to make decisions on how we measure. So we can actually take a variable that has the most amount of information, a continuous variable, and we can decide through using cut points or whatever sort of classification we want, we can boil that down all the way to the dichotomous or the dummy variable level. Right? So let's take something like income. Okay? Income is actually a dollar amount. Let's say we're going to measure it yearly. You get a yearly dollar amount. We know this because at the end of the year, or at least the beginning of the next year, we all file taxes. We're like, this is how much money I'm telling you I made. I actually made a little bit more than that, but you don't need to know about the rest. My cash tips. Right? Okay. So we can start out with a continuous variable. If you go online, my salary last year was $69,151. That's a continuous level of measurement. And that's not actually what I made. 2, how can I go from continuous down to categorical, some sort of ordinal level? What would I have to do? Think about how we discuss income. What sort of descriptive names do we give to different income levels? Okay. So we can come up with names for different levels. So we can talk about being in poverty. Is there anything under poverty? Extreme. Right. There's extreme poverty. There's poverty. Then what? College student. Is that in between the two poverties, or just slightly above poverty?
Above extreme poverty, to be honest.
A lot of college students out there that aren't actually attending college, but okay. Poverty. And I've seen some of the cars that you all drive. You drive nicer cars than I am. So let's add college student / faculty with kids. Okay, so poverty. What else do we have? Let's go into the classes. There's one under middle, though. Working class. Working class, middle class. There's an upper middle, which is when you make a lot of money, but you don't want to admit you make a lot of money, or your kids are really expensive. So you're upper middle class, where I make a lot of money, but I don't know where it goes. All right? Then you have upper middle, and then you have upper class, or you have rich, or you have Oprah money. Right? But what do we have to do? No matter what categories we create, what do we have to do? What do we have to do to assign people to these categories? We got to actually say how much amount of money it is, right? And that's the hard thing, because, people don't really like to be classified. They really don't, because I know you don't, because when I give you a grade, you guys hate that, okay? So we would have to actually assign dollar amounts to this, right? So from 0 to how much gets you out of extreme poverty so that you're making it and you're now in poverty. $10,000 a year? Is that poverty and not extreme poverty? Right? At what point do you go from working class to middle class? And remember, we're being precise here, so it could just be you're earning an extra penny. $39,999.99, you're working class. $40,000, you're middle class. Right? The difference is just a penny. But we have to assign values to these. Now let's say we don't really like this, right? We don't like assigning values to this, right? This is impolite. It's too much information to ask somebody, how much money do you make? Because that's impolite. So instead we can create these categories. But here's the problem with categories. People lie. So we can just simplify this, right? We can just make this a dummy variable. And we could say, do you have this standard? And what could it be? Yeah, what could it be? What could be the dummy variable way of asking somebody how much money they have? No. Okay. You could have one single number cut point. Right? One single number. Yes and no. Okay. Yes, general rule is to get the best data. The best data is the one that's more precise. Because if I collect down to the dollar amount, then I decide how to create the variable, right? See, I just did something. I want to make sure you all noticed it. There's a difference between data and variables. Data is the information. Variables is how you construct your data so that you can analyze it into a variable. Okay? How about this? Are you comfortable? Or we could flip it around. Do you have anxiety about money? Right? That's probably the lowest level we can get. Listen, I was like you guys. I was a poor college student. Tuesday nights were a good time for under $5. I could get Chinese food and a 40 from the corner store for $5. Tuesday nights were good. Okay? But it was $5, and I only had Tuesday night. Monday nights sucked. Wednesday nights were a little rough, because Tuesday night was a 40 a laser for $1.89. Okay? But at some point in your life, you stop worrying about, do I have to buy a $1.89 laser? So that's, for me, this would be my cut point. Are you comfortable with your income? The reverse of that is the idea of anxiety or stress. Right? Does your amount of income cause you stress? That's the simplest way I can think about in constructing a dummy variable from something that is originally very precise. Right? We can do the same way, right? Think about temperature. How do we discuss temperature? What's the temperature outside today? Marina? Hot. That's really all I want to know. Actually, what I want to know is, when I go outside, am I going to sweat? That's my dummy variable level. Is it sweat weather out? Is it jacket weather out? Which is when I'm talking to the kids. Kids, it's jacket weather. That's my cut point, okay? So, all right. So now to actually talk about what's in the book. So once you have data, you've created your variables, the next thing is, what do we do with it? Well, at the simplest level of analysis is just looking at your data. Just seeing what you have. One way to do that is through a frequency distribution table. This works best for categorical or nominal, ordinal, right? All of the non-continuous types of variables. And what you do is you take your category that you have your data in, and then you see how many times that category appears in your data. So this example is from the book. Something about how you select lottery numbers. Do you use a sequence? Because again, every number has an equal chance of being drawn. So if you're picking 6 numbers, why don't you just pick 1, 2, 3, 4, 5, 6? Well, why does my mom say you don't pick 1, 2, 3, 4, 5, 6? Because my mom sees a pattern, right? Which is the next option, right? Do you pick your numbers on a pattern? I should change this to test-taking strategies. How many people in here, when you're taking a multiple choice test, look at the pattern of the results, of your answers? Yeah, like you're done and you're looking it over and you're making sure you got everything filled in, and then you look at it and you notice something. There's 4 E's in a row. That can't possibly be right. There's a story of a professor who made every answer to a test A. And wanted, right? And you want to see what students will do. They know the correct answer, but will they allow themselves to turn in a test where every answer is A? The answer is no. Okay. So here are 4 different types of filling out a lottery ticket. Random is our friend Quick Pick. where you walk into the store and you're like, here's $20, can I leave with some lottery tickets? I don't want to know how this is done, just give me the lottery tickets so I can win the Powerball. Quick pick. Right, you get completely random numbers. In our data, our total is 22 people. We have 22 observations. And F stands for frequency, the frequency in which each one was picked. So what's the most popular method? The random quick draw, quick pick option. How do we know it's the most popular? It has the highest percentage. Right? Hopefully I don't have to teach you guys fractions. 12 out of 22 is 54%. Or 0.54 is a proportion. Okay. There, I just did teach you percentages. Okay. So if we're looking at this data, and we're interested in lottery selection method, anything stand out to you? Is there anybody here that in this data that you're curious about? Why the sequence person? What are they thinking? I want to know more about that person. Right? What is it that makes people go in and pick a 6-number sequence? I want to explain that behavior. That's what's interesting to me. All right. The idea behind a frequency distribution table is that you can take all of your data, and right here we only have 22 observations. So that'd be 22 different lines on an Excel spreadsheet. And we can condense it down into something that you can look at and understand your data. Okay. The other lesson for this week, the other video for this week, I asked you to take a look at a website that has data that you should use. If you're smart, you should use this for your course paper. It's I always just type in SDA, and it's usually on the first page. It's getting lower and lower every year. It's a website out of UC Berkeley. And what they've done is they've taken a data set and they've turned it into a website that you can search and download data from. So in its data archive, the two that I'm most interested in, one is the General Social Survey. It has better questions. The other one is the American National Election Study. It gets used all the time in political science and is routinely done around elections. So there's lots of interesting questions there about people's viewpoints on candidates and their voting participation and that sort of thing. So if I look at, this is the GSS. And I want to look at a variable. Here, I want to look at the variable called marital, which just asks somebody, hey, are you with somebody? What's your relationship status? In this data set, there are 62,000 lines. There are 62,000 people that have answered this question. How long would it take you to scroll down an Excel spreadsheet with 62,400 lines? It's like the never-ending Excel spreadsheet. Instead, we create a frequency distribution table, and we can see that most people in this survey are married. And then you have 21% that have never been married, single, or widowed, divorced, or separated. Okay. So here we have categories. We can take a look at our data. This is a frequency distribution table. This is the quickest way to look at your data. The first reason that you would look at your data is to go, did I type everything incorrectly? Right? So if I've got a 99 in there, and I don't know what a 99 stands for, what happened? It's probably a typo, right? It's probably a 9 that I just held the 9 down a little too long. Or I forgot to hit return. I got 2 9s next to each other. Or if I had a 45, right? Something might have happened with our data. So if you're creating your own data, a frequency distribution table is a way to look at it to make sure that it meets your expectations. Okay. The book talks about using bar charts. Don't. Do not use bar charts. I'm doing angry dad voice. Don't think about it. I'll put you in timeout if you use a bar chart. I'll take your data away for a week if you use a bar chart. Don't use a bar chart. Why? Okay, question mark. Why? Why shouldn't you use a bar chart? Look at it. Why shouldn't you use it? Yeah, this doesn't work for me. Here's the problem with the bar chart. The more bars you have, the harder it is to read. Flashback to middle school. You get a straight edge and you go, oh, 12. Because I don't know if that's 11 or 13 because my contacts are a little fuzzy and it's so far away. How would I know that that's 12? Instantly, by looking at it, if it were a frequency distribution table. That's how I know it would be 12 instantly. All right? This does not improve upon this. The fact that it can only make it worse. Because I've seen the way you park, you have no spatial reasoning skills. I see some of the clothes you wear. Sizing is an issue. Actually works for all of us. Right? You're looking at yourself in the mirror. How did you leave the house looking like that? And you want to create a bar chart? No. In my family, we do not use bar charts. Abby had to make one, and I'm like, sweetie, you should do a frequency distribution table first. Why? Because it's better. But Dad, it doesn't ask me to. But we're better than that. The Wood family doesn't use bar charts. And we sure as hell don't use pie charts. Because you know what's even worse about these things? Sure, they tell you the number. But it actually makes you think that this is something. It makes you think that 14 is something. Like, that's a reasonable serving size. It's not. It's only 14%. It's not a reasonable serving size. We're not cutting up the ice cream cake. Daddy gets a pattern size slice. John, sorry, you stink today. You get a sequence size slice. No, don't use these. Also, where is this information? It's in a frequency distribution chart. So you can make one table and not have to make two things that require you to have spatial reasoning skills. Also, when you do this color thing and you print it out, it's all just shades of gray. None of you here have color laser printers at home. You're like, oh, I'll do a teal one, and I'll do an orange one. No, it just all comes out as gray. Don't use these. The book also does this, which again, why? Why do two? You've got one. Just go ahead and do the table the right way. This is a histogram, which is different than a bar chart. How? The bars touch. Mm-hmm.
Elementary, middle school, and high school.
I know. I'm going through this with Abby right now. I'm like either the best father in the world or the worst father in the world, because my 9-year-old daughter knows what a scatter plot is, because that's the way you graph two variables. Gonna have to have a talk with Miss Bird. All right. Here's another one the book throws out there. This is a frequency polygon. No. Come on. Why do this? Here's the problem with these. They actually make you think that the difference between here and there is the line. It's not. There's no line. The line is made up. Because really all they're doing is this. Oops, that one was really bad. But they put a line in instead of a bar. Why? Because they want you to think it's a line. It's not. At least the book points out that some of these can lead you to make a wrong conclusion. And it has to do, this is the other thing that I hate, and that when I'm teaching generating these things, I always have to point out, these two figures here represent the exact same data. But what's the difference between the two? What do you mean the scale, Allie? Like, I know what the scale is, but what do they know what the scale is?
The scale on the left is 1 or 0.
Right. So the scale over here, is this the right one or the wrong one? Which one am I going to be angry at? Am I going to be angry at this one? No, I'm not. This is a yes. If you must, yes. This is a no. Why? Because it makes it look like there's actually a difference between Democrats, Republicans, and Independents. When there's not. How much of a difference is there? Well, according to this thing, there's that much of a difference, which is also why this is garbage. Because I should just look at this in the first place. Instead of getting out my ruler and drawing lines and trying to guess, well, the gap is this much for this. No. Just put the data as a percentage. Do it the right way. Okay. Another way that we can look at data, and this is more for our continuous data, is we can think about data not just in the frequency that it occurs, but also the way that the data itself is distributed across the range of values. This concept, even though it's only week 2, we're going to be dealing with distributions for the rest of the class. We're going to actually be doing this every class. So the idea behind a distribution is that we are showing you all of the data in its range and in its frequency as a curve. Okay. Now, looking at the curve, I actually do this when I teach like a big survey class, and I have, a couple years ago I had 80-something students in a class. Instead of looking at the table, I would just actually graph it out as a distribution. What's the curve of the distribution look like? And this is actually what you guys are talking about when you ask your professors for a curve. You're asking to curve the grades. You're asking the professor to make it look like a shape, which is what your SATs and ACTs and the LSAT and all the standardized tests, well, it's standardized by making the grades fit a curve. Okay. That'll come up again later in the course. But when you look at your data in terms of the distribution, you can get extra information out of it. One is the modality. So which one happens most? Well, the one that happens most are these peaks here. So if something is unimodal, it has one peak. If it's bimodal, two peaks, and multimodal means many peaks. We can also look at the distribution not only for the number of peaks or humps that it has, but also for the shape of it. Is it a symmetric curve? If something is symmetric, when we fold it in the middle on itself, it has the same shape. So back to the idea of grading curves. If something is symmetric, let's see if I do this right. I'm off a little bit, but F, D, C, B, A. If my grade distribution is symmetric, I should have similar numbers of A's and F's. So if you're asking a professor to curve your grade, what are most people going to end up with as a grade? C. Is that really what you want? Maybe. Right? It all depends on where you started out with, right? It's like, am I going to be in that C category? C is better than my D, but what if your D turns into an F? What if the professor was just really nice and he's like, oh, they're freshmen, they don't know anything, it's the first test, I don't want anybody to feel discouraged, I won't fail anybody. I'll just give all the F's D's. And you're like, no, we want a curve. It's like, okay, some of you D's might turn into an F. So your grade could go up or it could go down. Or you can have asymmetric distributions. And they can be skewed either towards the positive or negative. The skew is not in where the hump is, it's in the length of the tail. Right? You see this extra tail there? That's towards the positive side. That's a positively skewed. So that means there's more people with higher grades. If it's negatively skewed, there's more people with failing grades. Do you want your classes to be asymmetric? Well, if it's not asymmetric and it's symmetric, then equal numbers of people get A's and F's. Do you want your classmates to get F's? Maybe. You might want to. Could be a competitive program. Could be the fact that you realize that you're competing against those people for jobs and not this person. Maybe. You might realize that. Okay. These curves, like this, work better for types of data that are continuous and for data sets that are huge. Right? You notice there's not a lot of numbers here, like with the frequency distribution table. Why? Because I'm not looking for specific numbers, I'm looking for the shape of everything. Right? I'm not interested in how the individual grades are distributed, I'm interested in the overall class's distribution of grades. So you're not going to do this for everything. But it is an option, because today we're talking about how do we look at data? What kind of appearance does data have? And the shape tells us a lot about not only what the data looks like, but also where we are in the data, if we want to examine ourselves as individuals relative to a distribution. I think shoe size is like the perfect example of this. I have a hard time buying shoes. Does anybody else here have a hard time buying shoes? Or hate buying shoes? What's your problem with buying shoes?
Sometimes between a 10 and a 12, it's never 12.
He's between a 10 and a 12, but it's not an 11. Like, you got to go, and when you try on shoes, you get 5 different pairs. Because sometimes he's a 10, sometimes he's a 10 and a half, sometimes he's not an 11. Sometimes he's an 11 and a half or a 12. Like, dude, that's the difference between regular shoes and clown shoes. I have very wide and flat feet, but they don't have a lot of wide shoes out there available. Thank you. You've confirmed my life experience of 40 years. All right. So I think, when we look at shoe size or clothing size, like, these manufacturers are smart. There's a reason there's not a lot of 12s out there when you go shopping for shoes, because there aren't a lot of people out there that have a shoe size of 12. Anybody else in here have a shoe size of 12 or higher? 2. You guys. Maybe you can share shoes. Okay. Distribution of shoe size is more like the actual peaked distribution, where there aren't a lot of people out here at 12, but there's a hell of a lot of people out here at 9. Right? Raise your hand if you have a shoe size of 9-ish. All right, the men-women thing don't really work, though, does it? All right, so maybe it's not the best example, but still. Or clothing. All right? Anytime you go to Costco, there's a lot of larges. There's not really a lot of triple extra larges. I don't even know what color that sticker is on the clothes. But there's always mediums and larges. Nothing that definitely does not fit me. And that's the bulk of it. That's the highest part, right? This is a lot of the volume. We all wish we lived in a flat world where we had equal chance of finding the triple X extra large 12 shoes, right? Think about how awful it is to be Shaquille O'Neal. Dude's like what, 7'6", 7'4". His shoe size is in the triple digits. You know he's not going to Foot Locker to look for the newest Jordans that are released, because they're not going to have his 32 size foot. All right? Like, this is Shaq. Shaq's way out there. But Shaq wishes he lived in this world where he had about an equal chance of getting things out there, right? So the shape of the distribution also can show us how variable it is. In a peaked distribution, you don't have a lot of choices. You don't need a lot of choices because most people are in the middle. But with a flat distribution, where everybody is spread out, and we're all different, that's better because if you're out here, this is higher than being way down here. Right? I'm out of time, but I want to end on this. This is going to be probably the most important thing for us this semester. It's called a normal distribution. And this is going to be what we deal with probably from weeks like 3 to 10, is cracking this thing and understanding it. And you've all seen it before. I know you have in math. It's also known as a bell curve. And I'll pick up with this next class. All right? So right now I'm going to go compile the video. I'm going to look at quiz for section number 2 and turn that on. Don't forget you can do the quiz section exercise online. All right? See you next Thursday. Watch the other video. Play with the data website.